Assalamu alaikum. Let us start with a new topic, steady state stability. Let us say we have a generator which is connected to an infinite bus through a reactance X. And the swing equation for this system is given by like this: m del square delta by del t square is equal to Pm minus P by m is equal to h pi. Actually should have been g h by pi f, and h by pi means in per unit. So I can write it as, and Pe is equal to Ev x sine of delta or P max sine of delta, where P max is equal to Ev by x. So this is the P delta curve. In this case, this is the motoring mode where this delta is negative and power will be negative. And from delta is equal to 0 to 180, it is in generating mode. Let us say our system is operating at this point where delta is equal to delta naught, and electrical power that is generated is Pe naught. Now when delta is changed from delta naught to delta naught plus delta, that means slight increase in delta, the electrical power will change from Pe naught to Pe naught plus delta Pe naught, delta P. So when delta is changed or increased by some angle, this Pe will also increase by some electrical power. So this point will shift to this point where delta is equal to delta naught plus d delta, and this Pe will be equal to Pe naught plus delta Pe. I can write this change like this in terms of delta. This delta Pe can be written as d Pe by d delta. That's the differential of d delta at this delta is equal to delta naught multiplied by d delta. This is the mathematical term which we can convert this change into, or we can say where we can relate this delta Pe and delta delta through this relation. So from swing equation, now since delta Pe has changed, I have to replace this Pe by Pe naught plus delta P, because now this Pe has changed to this value, that is Pe naught plus delta P. So that is Pm minus Pe naught plus delta P, that's Pm minus Pe naught minus delta Pe. Since we know that at this point, initial operating point, this Pe naught will be equal to Pm. Pm is the mechanical power, and there is no mismatch between mechanical power and electrical power, and it operates in synchronism. So that means this is equal to this and this term will cancel out. This m del square del delta by del t square will be equal to minus delta Pe, because this Pm is equal to Pe naught and delta is equal to delta naught. One thing you should also keep in mind, that instead of delta I have used delta delta because I want to find out the value of this delta delta rather than the actual delta. I want to find out this d delta delta rather than the actual value of the delta. That's why I have slightly changed this swing equation like this. Now, okay. Now I will take this term to this side. It will be equal to m delta square delta delta divided by delta t square is plus delta P is equal to 0. That is this equation. And since we know what is the value of delta P from this equation, so I'll write down this delta P as dPe by d delta at delta is equal to delta naught into delta delta, that is equal to 0. Here I will take this d delta as common. So m d square dt square plus dPe by d delta at delta is equal to delta naught, bracket closed, delta delta will be equal to 0. Let us say this d by dt is equal to capital D, and d square dt square is equal to dt square. So this equation will then becomes m, because this d by dt square is equal to dt square plus dPe by d delta at delta is equal to delta naught into delta delta is equal to 0. Rest will be same. This term you will see will be a constant, because when we differentiate this p delta curve with respect to delta and put the value of delta, it will be a constant term. So here it will be this k1 d square plus k2 into k2 into y is equal to 0, while this k1 will be equal to m. You can see it from here. K1 is equal to m. This k2 is equal to dpe by d delta, and delta is equal to delta naught, and y will be equal to d delta. I just want you to recall this is a second order differential equation, and usually you have done them in terms of x and y. That's why I have written over here the y, because here y will be this y-axis, and here it will be d delta. I just want to find out this d delta with respect to time. How this delta change with respect to time. In earlier cases we find the value of p with respect to delta, but here we have to find the value of d delta with respect to time. So that's why here d delta will be on y-axis, and on x-axis we will be having t. That is why this independent variable here will have t. So it will be md square plus, sorry, k1 d square plus k2 into y is equal to 0. This is second order differential equation. You can so here k1 is equal to m, k2 is equal to del dp by d delta, and delta is equal to 0, and y is equal to this d delta. So the characteristic equation of this differential equation is k1 d square plus k2 is equal to 0, and its roots will be equal to d equal to, when k is taken to this side, it will be minus k2 divided by then k1 raised to power 1 by 2 plus minus 1 by 2. So it will be minus k2 by k1 raised to power 1 by 2. These will be the roots of this characteristic equation. So writing the actual value of the k2 and k1, so it will be plus minus minus del pe by del delta, sorry, del delta, delta is equal to delta naught divided by m. K1 is m raised to power 1 by 2. This is an important result because this will tell us what will happen, what will be the behavior of the output delta as it's independent on these values, that is this value and this m value. The observations on the roots of characteristic equation. The first thing is that this will always be positive and will have some finite value, but this may be del p by del delta, it may be positive or negative depending upon the value of the delta. For example, if del p by del delta and delta is equal to 0 is greater than 0, this k2 will be positive, this k2 will be positive, and the roots will be purely imaginary, because this will be minus some positive value minus some constant, that is square root of minus constant, it will be an imaginary number. So purely imaginary and conjugate, one will be let us say plus j something plus j k1, other way plus j some c, another only plus minus jc. So they will be imaginary and conjugate, and the system will be oscillatory about delta naught. It will oscillate about the delta naught. I will show that also to you, and hence the system will be stable for small changes of power. In this case, the system will be stable. Now let us try to find out how it is oscillatory, what will be the actual response. Now d is equal to plus minus j root of k2 by k1, because we are assuming k2 to be positive. When it is positive, here it has the minus from the formula, and that has been taken out, and it will become j. So it comes out to be this k2 by k1, this minus root of minus 1 is taken to be out as j plus minus root of k2 by k1. We know that for a complex roots, if d1 is equal to alpha plus j beta, d2 is equal to alpha minus j beta, then y is equal to, it is actually the solution, in general solution of this equation, then y is equal to e raised power alpha t c1 cos of beta t plus c2 sin of beta t. For our case, alpha is equal to 0 because it's a pure imaginary number. Beta is equal to, so d1 is equal to j beta and d2 is equal to minus j beta, where beta is equal to square root of k2 by k1, and y is equal to delta delta. So finally, this y is equal to, when alpha is equal to 0, cos of beta t plus c2, sorry, c1 cos of beta t plus c2 sin of beta 2, where the c1 and c2 are the integration, sorry, constant of integration. So the final, after putting the value of beta in this equation, it comes out to d delta is equal to c1 cos of square root of k1 by k2 into t plus c2 sin of square root of k2 by k1 into t. From here I can get the actual relation of delta delta by having the initial values. at t is equal to t naught, that is the switching instant. Let us take it to be equal to 0. At t is equal to 0, this delta delta is equal to 0. When we put t is equal to 0, that means this whole term will be equal to 1, this whole term will be equal to 0. That means c1 will be equal to 0. That means this whole term will vanish. So delta delta will be equal to c2 only, c2 sine of square root of k2 by k1 into t. Where you can find out the value of this c2, it will be simply delta delta max. So final relation will be delta delta will be equal to delta delta max sine of this under root of k2 by k1 into t. So okay, this is the same equation, and putting the value of this delta delta will be now equal to c2, this delta max sine of square root of del p by delta at delta is equal to delta naught divided by m into t. This will be the actual solution. This term will be equal to 0. I have not written that. I have written both the terms, but when I put the initial condition, this term vanishes. Only delta delta will be only this term. So what is the frequency of oscillation? Since this is sine of omega t, this will be the frequency of oscillation, omega. You can find out this omega. So here omega will be equal to k2 square root of k2 by k1, that is square root of del p by del delta at delta is equal to delta naught divided by m. This will be the frequency of oscillation, angular frequency of oscillation. You can get the frequency by simply dividing this equation by 2 pi. Now this is the actual value of this actual variation of the d delta. This is at t is equal to t naught. This is the switching instant, or we can say when the disturbance occurs at t is equal to t naught. This is actually nothing but a sine curve, and this is d delta max, this value. So this is when del p by del delta, delta is equal to 0 is greater than 0, and here we are assuming that the damping is 0. When there is, usually our system has some inherent damping, and these oscillations will finally damp out, and this delta will settle down to any value, final value, and d delta will be delta will be equal to 0. So that can be shown like this: the oscillations with some damping, and finally it will result that d delta will be equal to 0. This is d delta 0 before the transient occur, or we can before the change, before the disturbances occurs. This is after that, and when after the finite time, this d delta will again settle down to 0, and then we can say that this d delta, this our system has now become the stable. This can be shown also like this. This is delta naught, and this will be the delta naught plus delta delta that I have shown. That is the actual value of the delta. Since I have told you that we are not interested in that, that is this delta naught plus delta, and I have written it somewhere. This there will be the oscillations of this delta around this delta naught. You can see this is when delta pe by delta delta is greater than 0, and after if there is certain, since I am assuming that here the damping is 0, if there is certain damping, when there is damping, these oscillation will settle down, and this delta will come again, will be equal to delta naught. So this is the actual variation of the delta naught. This is not the delta delta. So the second observation is, if delta pe by delta delta at delta is equal to delta naught is less than 0, that means k2 is negative, the roots will be real. One will be positive, another will be negative, but of equal magnitude. You can see it from here. Here, if this is negative, minus into minus is plus, that means this roots will be real, and d will be equal to plus minus some real value, that is square root of k1 by k2. So in this case, delta will increase without bound upon the occurrence of small power increase, and synchronous will be lost. It means even if there is a small increase in the power, you can see that since this delta is increasing continuously without bound, the synchronism will be lost. Thus, the system will be unstable for delta p by delta delta at delta is equal to delta naught is less than 0. So that means when delta p by delta delta is greater than 0, system will be stable. When delta p by delta delta is less than 0, system will be unstable. So that means g1 is equal to root of k2 by k1, and d2 is equal to minus root of k2 by given, and the solution of this will be equal to delta delta c1 e raised power k2 by k1 into t plus c2 e raised power minus k2 by k1 into t. The second term as it has minus, as t increases this will finally vanish. It will come down to 0 very fast because it's an exponential, but this increases very fast. This increases very fast. We can see that second term can be neglected. Delta delta will be equal to c1 e raised power minus k2 by k1 into t. So you can see this is increasing continuously without bound. So this is the value of delta. Delta, it is greater than 0, and when delta p by delta delta is less than 0. So this delta p by delta delta at delta is equal to delta naught is known as synchronizing coefficient or stiffness of the synchronous machine. It gives us the slope of the power angle. That we know, because differentiation of any curve with respect to independent variable will always give the slope. This will also give a slope. This is also known as synchronous coefficient or stiffness. The more the value of this, the more is the stiffness of the synchronous machine, and more is the stability. The more the value of this delta p by delta delta, which is greater than 0, can be equal to 0.1, 0.2. If the value of this is more positive, the more the stiffness, the more is the stability. For a constant value of v, e, and x, delta pe by delta delta, which is greater than, will be greater than 0 for delta from 0 to 90 degrees. So we can say that the system will be stable for 0 to 90 degrees, and the system will be unstable for 0 to 180 degrees, because for this case this delta delta by delta pe by delta delta will be less than 0, which can be again shown by this curve. You can see from this point to this point the slope of this curve is positive, that is delta pe by delta delta will be positive and the system will be stable. For delta is equal to 90 degree to 180 degree, delta pe by delta delta is negative, so that we can say this curve will be this part of the region of this curve will be unstable. The maximum power that can be transferred without losing the synchronism is at delta is equal to 90 degree. This is the maximum power that a synchronous machine can transfer without losing synchronism, and this is known as the steady state stability limit, that is the Pmax. The more the value of this Pmax, the more is the steady state stability of the synchronous machine. One more thing that I would like to tell you, because you can see from here, let us say I will go back to the actual value, actual diagram, that is this. Since we have changed, let us say power has changed from this point to this point, we are changing deliberately the mechanical power from this point to this point. So mechanical power has changed. Now delta naught is still delta naught, and we know that mechanical power has changed, but just a minute. Okay, I'll try to explain it from here. That is this. Let us say mechanical power has changed from this part to this part. We're not changing the electrical power. This was the change in electrical power due to change in delta. But I'm saying that I'm changing the mechanical power input to the generator. Let us see what will happen to the electrical power. When I increase the mechanical power from this point to, let's say, this point, so here mechanical power is more, but electrical power is still this much. So in this case, when mechanical power increases, we know that PA is equal to PM. This PA is equal to PM minus PE. Since PM is more, it results in the acceleration of the rotor. And we know that FR is ahead of FSR, and we know that the delta is between them, and their speed is in the same direction. When FR is now rotating, accelerating, but Fr is rotating and the synchronous speed, this delta increases. When this delta increases, this electrical power also increases and it balances the mechanical power, let us say at this point. Let us say I am still further increasing the mechanical power to this point, from this point to this point. Now here is this, the synchronism has again taken place at this point. Mechanical power is now equal to electrical power because delta has increased now. Now I increase the mechanical power again at this point. Now what will happen? The acceleration occurs again and the rotor will start rotating more than the synchronous speed because it is now accelerating. Delta will increase now. When delta increases, P also increases so that it comes out to be equal to again P max. Let us say after that this P M I have make it equal to P max from this point to this point. Again there is an acceleration. Rotor accelerates first. When it accelerates, this delta increases. This delta increases in such a way so that this P becomes Pm and then this acceleration goes to 0 because now this P becomes equal to Pm, acceleration becomes 0. When we further increase Pm, since again the same thing happen. When Pm is increased beyond this, Pm will be more than the maximum of the Pe. So when Pm it results in the acceleration of the rotor. Again this rotor will accelerate, again this delta will increase, but now instead of increasing this electrical power, this electrical power will decrease. When this electrical power decreases for increase in delta, this Pm minus Pe further increases because this has now the increased value. This Pm, instead of increasing, it now decreases. The difference of these two increases. That means it results in more acceleration of the rotor. When more acceleration happens, there will be more increase in delta. When more increase in delta happens, that means Pe will decrease further. When Pe decreases further, this difference increases further, more acceleration in the rotor, which results in the speed of the rotor and synchronism will be lost. That is why till this point, since delta increases, which results also in the increase in Pe, this is the stable region from this point to this point. The more the value of this maximum value, the more the stability of the synchronous machine. After that, since Pe decreases as delta increases, the system becomes unstable because there is no available electrical power for increase in delta. Actually, the speed decreases as increase in delta, which results in the this losing of the synchronism. So I hope you understood this, how this happens, and we finally conclude that the system will be stable for 0 to 90 degree and system will be unstable for 90 to 180 degree. So there is one more explanation which I have just given to you. Please try to understand that. If you haven't understood that, let me know. I will try to make it more clear. So to have the higher stability, we should have higher values of this E, V, and lower values of X. That is why we make the system, we increase this voltage level. This is one of the reasons to increase the voltage level to make the system more stable and to decrease the value of the X. We use the bundle conductors as well for this case to increase the reactance of the X. This is one of the reason for the bundle conductors. The prime reason for bundle conductors is to reduce the corona loss. Now let us try to do one numerical based on the same explanation. A synchronous generator of reactance 1.2 per unit is connected to an infinite bus bar where V is equal to 1.0 per unit, that is the bus bar voltage, through a transformer and a line of total reactance of 0.6 per unit. Okay. The generator no load voltage is 1.2 per unit and this inertia constant is 4 megajoule per MVA. The resistance and the machine damping may be assumed negligible, that we have usually done. The system frequency is 50 Hz. Calculate the natural frequency of oscillation if the generator is 50% loaded. So first let us calculate M. We need to calculate this, that is omega, that is del P by delta, delta is equal to delta naught divided by M. So this is the equivalent circuit our system. This is synchronous generator whose terminal voltage, not terminal voltage, excitation voltage 1.2 angle of delta. So this is the synchronous machine reactance, that is 1.2 per unit, and this is the reactance of the line and the transformer, that is 0.6. This is the voltage of the infinite bus. So first we'll calculate M is equal to H by pi F, that is in per unit. H is value of 4, pi is into pi into 50, it comes out to be 0.0254 seconds square per electrical radians. I hope you understood this. Actually it should have been megawatt per unit because this is in per unit value. Megawatt per unit second square per electrical radians. So this is M. The first case is that 0.50% loading. That means P is equal to 0.5 Pmax. Pmax is the steady state stability limit. So P is equal to Pmax sine of delta. We know this is the electrical power equation, but this is equal to 0.5 Pmax. That means 0.5 Pmax is equal to Pmax sine of delta. This Pmax can cancel out. This sine of delta naught is equal to 0.5. That means delta naught is equal to 30 degrees. Again, writing this P is equal to Pmax sine of delta. That is E V by X, because Pmax is equal to E by X sine of delta. That is 1.2 into 1 divided by 1.8 into sine of delta. It comes out to be P is equal to 0.67 sine of delta. So del P by delta will be equal to 0.67 cos of delta. That means differentiation of this. Now this has to be calculated at delta naught. Delta naught is 30 degrees. Put the value of 30 degrees, you can get the value of 0.577 megawatt per unit, because we are dealing with per unit. This is the per unit value per electrical radian. So this is the value of del P by delta naught. Delta is equal to 30 degrees. So omega is equal to this del P by del delta, and delta is equal to 30 degrees. That is 0.577 divided by m. M comes out to be equal to this value. So this comes out to be this 4.7 radians per second. But when frequency is calculated, we have to divide it by 2 pi. It comes out 0.575 hertz. You can see, since there is a change, there is a difference of 50% from the Pmax. This is more. Now if P is equal to 0.8 Pmax, 0.8 Pmax is equal to Pmax sine of delta. That means in this case, this should be delta naught. Delta naught will be equal to 53.1 degrees. Now P again is equal to 0.67 sine of delta. Del P by del delta is equal to 0.67 cos of delta at 53.1. Del P by delta is equal to 0.4028 megawatt per electrical radians. So putting the value of this del P by del delta in this equation, M is already calculated. This comes up to 3.9 radian per second, and F is equal to 0.633 hertz. So in this case, you can see it that the frequency of oscillation is less, as PE is slightly lower. The difference of PE and Pmax is only 0.2, that's 20%. As you go higher, the frequency of oscillation will be very small. Now, methods of improving stability. Stability, how to increase the stability. To increase the stability, we need to increase the Pmax. We have discussed it. More the value of the Pmax, more will be the steady state stability, because more will be the steady state stability limit. So to increase the Pmax, we need to increase the excitation of the generator, that is E, or by operating the system at higher voltage. That means this V, that is the higher value of E or V or both. We can increase the voltages. By using the decreased value of transfer reactance, that X can be reduced by using the parallel lines. When two parallel lines are used, the equivalent reactance will be reduced. Using the bundled conductors, again we know that the reactance of the bundled conductors is less as compared to unbundled conductors. And using the series capacitor, we can use the series capacitor, and we know that reactance of series capacitor will decrease the overall reactance of the line, because total reactance will be XL minus XC. So this also helps in reducing the reactance and hence increasing the stability of the system. I'll stop here and